Oh my gosh, OChem1, can you believe it? This is going to be our last video for this semester. I can't hardly believe it. We are going to end our semester on some aromatics, resonance, and synthesis. We've got to start with resonance in order to understand our synthesis. So let's take a minute and let's draw out some of the substituted benzenes we made in the last video. So it's one thing to just start with our benzene. Okay, if we look at our electrons that are in that aromatic ring, it's nice and straightforward to see that they are sharing between all 6 of those carbons, so we can draw our resonance there and there. And what a resonance structure tells us, let's go back to Gen Chem 1 for a minute. What our resonance structure tells us is when our electrons are sharing over more than 2 carbons. So we're literally spreading out those electrons. When we first started drawing Lewis structures, it was assumed that electrons shared between 2 carbons. Well, as we've seen throughout our organic history, that's not necessarily the case. You can have pi electrons that share over more than 2 carbons. So the correction to that is to draw resonance structures. Now, the old way to draw, so if you're looking at some pretty old benzene things, you'll sometimes see that. That will be drawn as a benzene. Now, that's a whole lot easier than drawing this type of resonance structure. So why the change, right? Why do you draw 2 structures that just look the same? Because in this resonance structure, you don't really know how many electrons are being shared across those 6 carbons. But yet in here, you can count, okay, it's actually those 6 electrons. And we've known now since our Huckel rule that that's actually really important to know how many electrons are there. So this is the newer resonance, and that's what we're going to use, and that's what we're going to draw. And you notice in that overall resonance, you end up back where you started. So you can have multiple resonance structures, but you're really just tracking where those electrons are sharing. Now, in real life, are your compounds flipping back and forth between these two? No, not at all. They're not 2 different things. You're showing where your electrons are over that whole compound. You're looking at it as a whole. So let's take something we just made in our last video and let's draw some resonance structures. And it's going to be extremely important. It's going to explain what we need in synthesis. So I want to take the first one, and that is going to be aniline. So either aniline or phenol are going to look the same way. And I don't want to just start here. I want to literally draw out where everything is. Okay, so aniline is a pretty common reagent and starting material for things. Shoot, we have it in our lab. It's right on the shelf in there. So we need to picture aniline, where stuff is. Where are the electrons and where is electron density? Now, it's not just benzene. I'm sorry, my pencil is freezing. This isn't just benzene. I mean, this is, I'm going to plug my pencil in for a second while I'm talking because it is frozen. Okay. So it's not just benzene anymore. As soon as you add a functional group to your benzene and you have a substituted benzene, we always need to stop and think about what that functional group is doing to your benzene. So remember, we kind of pictured, and I know it's a gross picture way to picture this, but we're kind of picturing that aniline is like a racetrack of electrons. Well, what did this do to affect that racetrack of electrons? And we have basically 2 different options. We can either have electrons that donate into that racetrack, so they help it and they share with that racetrack, or we can have functional groups that take away from that racetrack. Something like aniline, you've got a nice glaring lone pair right there, right next to that benzene ring, and available. So they donate into that benzene ring, and that is going to shape what our resonance structures look like, and that's going to shape the overall electron density of benzene. Now, just straight benzene is very even. Those electrons are sharing even Steven around all 6 of those carbons. But the second you add something with a lone pair here into your benzene, you can now donate that in to your ring. So let's draw what that does to your benzene. And I actually want to draw these just a little bit easier to see. There we go. All right, so what happens when your lone pair from your aniline donate into your ring? Well, you can't have 5 bonds to carbon, so something's got to give. So these electrons right here have to move, and I'm going to put them right there to start. Now remember, the goal is to see how we've just disrupted our little racetrack. What did we do to it? Well, we just added right here. And I'm going to put that pair of electrons on that carbon, and that's telling me, I have electron density on that carbon, and it's not the same as the electron density on this carbon. Okay, we're not sharing even anymore. And then our other bonds have stayed the same, but the beauty with benzene and resonance is that we work our way all the way around. So you're not going to just sit with a negative there. You can now reform a double bond, and those electrons can go right here. And now, is this a true negative charge that we're forming? No, remember, we're trying to just show where electron density is, and we didn't develop an overall negative charge in our substrate because we have that positive on nitrogen. These are formal charges. We're showing how electrons are being shared. And look at that resonance structure. Now we've got electron density on that bottom carbon there. Okay, let's keep going. We're going to end up back where we started. That's your goal of a resonance in a benzene ring. So now we're going to put those electrons right there. Okay, so now we have here. We've just moved to here, and then now to here, and we have a negative right there. Okay, still a formal charge. We're not quite back to where we started, but we're almost there. So what happens if we reform this double bond? We give the lone pair back to nitrogen. So what we're saying and what we're showing in this resonance structure, we just put the lone pair back, and we just show that those electrons are sharing around that whole 6-membered ring. They're also sharing with that lone pair in that aniline. Oh, those are hydrogens, not methyls. Okay, we're sharing essentially all of those electrons are donating into the ring. So we have some vocab words here. The first thing is that because your lone pair is going into the ring, you are an electron donating, or sometimes called activating, because you just took a nice a nucleophile that was okay, not very good, and honestly, adding electron density in, you just made it better. But now if we want to picture our aniline as a nucleophile, let's get a little bit deeper. Our electrons are sharing around that whole ring, but they're not sharing even or equal. If we were to look at this in a map, and we would have just a generic benzene, we would see a cloud of electrons that's nice and equal, nice and even. if we look at our aniline, it's not going to be nice and even. In fact, we're going to have electron density where we drew those negatives. And we're going to almost be missing electron density in those other spots. So it's going to look totally different. So our aniline would actually be a really good nucleophile, but only on this carbon, and this carbon. That's where your negatives are. So what do we call those? When you've got a group, any kind of group on a benzene ring, okay, and let's just redraw that. On that benzene ring, we learned in the last video that this position is ipso. That is on the same carbon as where you substituted. All right, but what if we're going to use this in synthesis? That carbon's taken. And we just learned that there are certain spots, this one, and this one, that are going to have those electrons more of the time. So we need some vocab there. Next to whatever group you're looking at is ortho. Okay. 1 over is meta. And exactly across is para. If you ever watch Big Bang Theory, sometimes Leonard's t-shirts are organic chemistry jokes. And this is one of them. He had a benzene on one day. And he had different substitutions here. And then it would say something like here, meaning paradox, or, unortho, dox, and he had all kinds of jokes or whatever on his t-shirt. It was pretty funny. But I guess only an organic chemist would find that funny. So if you're looking at your aniline, what we just learned is that in the ortho or para position, this is going to be a good nucleophile. In the meta position, that would suck. So if you actually did a reaction with aniline, guess where your reaction is going to happen? Ortho, para. Okay, that's what that's telling you in synthesis. Literally, for the first time all semester, you get a table. Shut the front door. Okay, I stole this table from Mastering Organic Chemistry, so I give the link up here so I can give credit to that. So your link is right up here for this table. Let's find on here, here is our aniline and our amines, and they are here under strongly activating. And what that means is when they're strongly activating, they are going to be ortho-para directing. Okay, and then when they are down here under deactivating, so next we have nitro way down here under deactivating. We're going to draw that one next, and we're going to find that these are meta directing, meaning your next step will end up, oh, we need to do this because those are ortho-para. They are just funny, okay? So what that means is that in your next step of synthesis, it's telling you where your next group goes. So let's draw the other resonance so that you have it, and then let's apply this in a couple synthesis so you can get the hang of it. So let's compare then. We've got resonance for electron donating. Let's draw resonance for electron withdrawing. So let's get your NO2 group up here. Okay, now you have a nitrogen right next to your benzene ring for both of them. But what's different? Well, two things. One, this lone pair was available, was screaming right there, I'm available. Okay, now right here on this nitrogen, do you have an available lone pair? No. And not only that, you have very electronegative oxygens pulling electron density towards them. So you have the exact opposite situation in this benzene ring. In fact, you have something pulling electrons out of the ring instead of donating electrons into the ring. Okay, here's what I mean. You've got this whole electronegative group right there, more electronegative than carbon, and you don't have an available lone pair. So the only option is actually to draw electrons in towards those oxygens. They are the most electronegative atom out of that whole thing. So that is naturally where the electron density is going to end up. So for our nitro groups, we literally end up with, oh, I didn't mean to put a line there. I meant to put dots. So we literally end up with 2 negatives on those 2 oxygens. And remember that these are canceling. We're about to cancel, so wait for it. That looks like a whole lot of charges. We did not mess with these bonds yet, but we stripped electrons away from that carbon. So this bond right here, if you look at it, that bond is feeding into and drawing into the nitro group. That's leaving that carbon just a little bit high and dry there, a little nudie kabooty. So look at right away, our charges are the opposite. Okay, so our nitro group is not electron donating. Electrons aren't going into the ring. We are electron withdrawing. And those are deactivating. So if you are looking for this to be a nucleophile, you made a crappy nucleophile much worse. So you just took a crappy benzene and you made it much worse as a nucleophile. Will it still work? Yeah, but you're going to have to really, really have a kick in the pants reaction in order to get that to work. So how do we then go around our ring? Well, you've got a carbocation here. You're going to fill that space in. It's not just going to sit there. Give me 1 second to draw all of those charges. Okay, so we can fill in our space here. That stripped the electrons from that carbon. Okay. And then, let's keep going. So we then can take these electrons and fill in that space. Let's see what we get. All right, let's add some charges there. Okay, so we just made a bond there. We left a carbocation right there and missing some electrons right there. Okay, then how do we fill in that space? Well, remember, we've got to get back to where we started. A resonance for benzene goes all the way back to where you start because you're just showing electron density. Okay, so we have to actually go all the way back to our oxygen and then put those electrons back. So now we're back to where we started. We have just gone all the way around the ring. And we have our nitro group. And, oops, I hit the wrong button there. And then we reformed that bond. There you go. All right, so now let's talk turkey. If we want to use this compound as a nucleophile, well, first of all, it's going to be a harder reaction. You just made a crappy nucleophile worse. But you need electrons to form bonds. Okay, it was easy on the top one because we made our negatives, right? We had negative in our resonance. So that meant we had electron density there. So you did the opposite in electron withdrawing. In fact, you were showing where electrons aren't. So in this bottom resonance structure, ortho-para is where you don't have electrons. So the only option for these to be nucleophiles is actually in the meta position, because those are the only positions that you still have electrons. So both of these are equal but opposite. That top resonance structure, you had negative charges, and your negatives end up orthopara, and you're using it as a nucleophile, so you need electrons. And then in the second resonance with your electron withdrawing, you literally still have your charges orthopara. It's just that your charges, that you're missing electrons, not that that's where electrons are. In fact, you don't have electron density there, so it can't be a nucleophile there. It has to be a nucleophile meta. So if we go back to our chart then, that's why on this side of our line, okay, everything after that group will be meta. And then on this side of our line, everything will be orthopara. All right, so let me show you what that means. Let's do some synthesis and let's have some fun with it. I want on this video to make 2 different compounds. Let's make some old chemicals. Let's use some fun benzene chemistry to do it. The first one I want to make is TNT. And TNT stands for trinitrotoluene. Let's draw the structure. Toluene is that methyl. Now this is not something that you are just going to be able to do at home. We could do it on paper, but not at home. And why? And we're going to see why in just a second. Okay, so first of all, let's double check our little chart from our last video. Okay, we're starting from benzene, we're putting on a methyl group, and we're putting on an NO2 group. How do we do that? Well, let me just write out the reactions so we can remember from the last video. How do you put a methyl on a benzene? That's our phenyl crafts. So I would draw this. Okay, that's our toluene. We just made toluene. In fact, let's write that. Toluene is also another big industry. Okay, toluene has similar properties to benzene as a solvent, but it is not a carcinogen like benzene is. So it is still a big industry. Okay, and then how do we add nitro? We saw that in our last video. That is our nitric acid and our sulfuric acid. That is how we add nitro. Okay, literally, we're just going to mix and match these 2 steps. Okay, so how hard is that? Well, we have to keep in mind that the second you put something on benzene, we now fall into these resonance structures, and we have to use our table. All right, let me show you what I mean. When you have benzene, you can add your methyl group wherever you want because you have symmetry and everything is even. But once you have a methyl on there and we want to add the next step, okay, so let's say I take this one and I'm ready to add a nitro group. Now I need to check the table. All right, once you have a group on your benzene, you use the table. Let's scroll down and look at that table. Let's find our methane on the table, and we're going to look at 2 things. Where is methane? Here it is. It is activating orthopara. All right, I'm going to scroll back up and write that down. So we are activating and orthopara. That means that your nitro group will end up ortho or para. Dealer's choice. You can pick which one. And that reaction, because it's activating, won't be too bad. You're helping that reaction just a little bit. So let's put that first nitro group, ortho, and let's go check our structure of TNT. Is that matching? It is. Okay, now let's compare if we do nitro first, and then we'll write the whole synthesis out. Okay, now that you've got nitro on your benzene, you go check your table. All right, let's check our table. Our nitro group, remember, is way down here, strongly deactivating, and it is a meta director. So let's write that down. It is deactivating and it is meta. So that means our next step is going to suck, right? We just took reactivity away, and our next step has to go meta. So if I'm ready to put my methyl group on, guess where it's going to go? It will go meta to our NO3, which that is ortho, meta, para. Okay, so let's put our methyl group here. That is meta. Is that where we need it for TNT? No, our spacing is wrong. So that's what I mean by reading the table. So if you're going to make TNT, how are you going to do it? You can't use this bottom setup. Mother Nature's against you. It's not going to work. You have to use the top one. So let me show you how TNT is actually made then. Okay, we make our toluene. That's a 1. Okay. So we're going to make toluene. And then now our toluene is an ortho para director, and it's activating. So that next step is not too bad. So now we've got our nitro group, and I just chose that ortho position. But now you put an NO2 group on there. Okay, now you have 2 groups. Well, son of a motherless goat. How do you read the table if you've got more than one group? Strongest one wins. Let's go to our table, and we're going by strength. So our methane is kind of in the middle, but our NO2 group is way down here, strong. So NO2 is going to win. So let's go back up to our synthesis, but it's also deactivating. So our next step is to add another nitro group, but honestly, you just made this reaction suck. So the only way it's going to work is if you actually use an awful lot of heat. And I mean a lot of heat. You're going to have to really make that work. And then where is your next NO2 group going to go? Well, you can choose either meta, but remember now it's going to be meta to your NO2. So that's here or here. So let's just work our way around the ring. Let's go ahead and put it here. So now, holy crap, you've got 3 things on there. Your NO2s are the strongest. You made a sucky nucleophile way worse. So the only way to actually make that TNT and do that next step and add that last nitro group is that you are actually going to need not just an extreme amount of heat, but you're going to have it under pressure as well. So now we've got NO2 in both of those places. Well, what's left? Okay, meta to your NO2 here is right here. And oh, lucky for us, they work together. That's meta to both of them. So this is where your last NO2 group is going to go, and that's your synthesis of TNT. Okay. So whatever you do for this next test, you definitely need this table to help you in synthesis. Now let's end with one more. Let's make propofol. Okay, propofol is a favorite of mine. It's just fun. Okay, propofol looks like this. No it doesn't. Looks like this, and we have 2 isopropyls right here. Okay. All right, so let's start from benzene, and let's just do what we did before. We just have to mix and match those 2 steps. How do we make the phenol? We use that cumene process. There's our phenol. And then how do we put an isopropyl group? That's our phenyl crafts. We can start with this one or this one. either one. It's going to rearrange. That's a nice carbocation rearrangement. And there is our isopropyl. So let's do the same thing we did for TNT. Let's make sure we have them in the right order. Okay, so I'm going to check my table. Remember, your second step is where you check that table. So phenol is one of our strong ones, and it is orthopara. Orthopara, okay? And our isopropyl is one of our alkyl groups, and that is also orthopara. So our phenol is actually pretty strong, and that's going to be the better nucleophile. So honestly, I would take either answer, but I'm going to go ahead and start with the phenol. And then, so let's take and let's make that phenol. And now we just made a crappy nucleophile better because we just made that more reactive with our phenol. And now our next step is going to go orthopara. So I'm going to add right here. And that next step, ortho, right there, ortho to your phenol. And then can't we turn right around and do that again? We can. But now guess what? Strongest one wins. So which one is the strongest? It is the OH group. And so that will be orthopara. So let's turn right around and do it again, because what is ortho or para to that OH group, here or here? And that is where we want that group. So we've got, now we just made propofol. All right, so I hope this gives you at least some ideas on how to read that table and how to tackle just a little bit of synthesis. We can mix and match, and you can do some of that homework. And I guess I will see you guys soon in the Zoom sessions, and we can do some synthesis and try it. So have fun. You might want your own table. I just kind of stole this one so I could have something to write on. But you may want your own table. I think I even have one posted on Blackboard for you. But start to have fun. I find this synthesis easier than what you just did on the last test because